going to be investigating the strategy known as related rates, which has for the past several years shown up as an application problem on the AP Calculus exam. It's almost always on the multiple choice, and it's been making an appearance during the free response portion in the past several years, and so it may just show up as one of, or part of one of the free response questions this year as well. We want to be prepared for that. It's also a big application of differential calculus. What I mean by differential calculus is calculus involving derivatives. The calculus of derivatives, rates of change. We saw in our related rates packet, the 4.9 packet, which is part of your OTL, how when we have several related quantities that are changing, that are each changing with respect to time, then it's an opportunity for a related rates problem. Today we're going to nail down a strategy that will allow us to carry out those problems to their end and be able to answer questions like how fast is the distance between Phoebe and Terrence changing when Phoebe is 200 meters from the intersection, right? We'll be able to determine that at what instant that instantaneous rate of change is using our related rate strategy. So I'm super excited about that. As you organize your lives, right, and plan for big upcoming events, please note that a week from yesterday, next Monday, 11/16, is our Unit 4 test. And so today we'll be investigating related rates. Next class will be kind of a structured review day, and so you'll have some time in class to work and review with a classmate. And then that's leading up to our Monday, November the 16th, A-Day will be your Unit 4 test. And again, that'll be a big one, 2 parts, and there's a Unit 4 concept and skill guide that's already posted online on our Unit 4 blog. So make sure you're checking that out. You will get a hard copy next class, but if you want to get a jump on that, you can check out the digital copy on our Course Moodle website. Questions about that test date? Okay, then let's go ahead and get going. If we're given an expression, a relation x cubed y to the 5th plus 2x equals 34, and we're going to write an equation of a tangent line. First, is this an implicit or an explicit relation? Go ahead and tell the class when I call on you. So is this an implicit or an explicit relation? Paul?
Implicit.
Implicit, how do you know?
The x and the y are on the same side.
Absolutely, we've got x and y's mixed up on the same side. All right, now this one we could differentiate explicitly, but we would first have to solve for y and rewrite, right, and then determine what kind of rule we'd use, and that's going to be much more complicated than if we just go right now and generate our y prime, our dy dx, using implicit differentiation. So let's go ahead and do that now. We'll go ahead and differentiate term by term with respect to x on both sides. When we do that, we'll have to utilize the chain rule. Every time we differentiate a y power with respect to x, it's going to spit out a dy dx, a y prime, a times the derivative of the base. Let's go ahead and try that. So overall, we're going to use the product rule to differentiate that blue squiggle underlined term, x cubed times y to the 5th. I know the derivative of a product of two functions is the derivative of the first times the second plus the first times the derivative of the second. And here's where we get to use our chain rule. The derivative of that y to the 5th with respect to x is exponent times the base raised 4 and less, and then times the derivative of the base. What's the derivative of y with respect to x? That's my dy dx or my y prime. So every time we differentiate a y term with respect to x, it'll spit out a y prime. Meanwhile, back at the hacienda, we're still differentiating term by term. We've got the derivative of 2x with respect to x. That's just 2. And then on the right-hand side, don't forget the derivative of that constant is 0. Everybody got that right on your rules quiz. Woohoo! Both parts, right? Both on the symbolic and the verbal, so that was good news. And now we've generated our expression. What do we want out of this expression that's going to help us with our equation of the tangent line? So what term do we want to solve here for? Jake?
You want to solve for y prime.
Absolutely. So we need that y prime so that we can generate the equation of a tangent line. Y prime still represents, right, the slope of the relation at any given point along it. We'll just have x's and y's in my expression for y prime. All right, let's do it. So what are we going to have to do? Yikes. We're going to add or subtract, right, to get all the y prime terms on one side, everything else on the other, and then multiply or divide to isolate the y prime. So it looks like we can subtract over that 2, subtract over that 3x squared y to the 5th, and we'll keep the y prime x cubed times 5y to the 4th on the left. Make sure I get my signs correct here. Subtract over the 2, subtract over the 3x squared y to the 5th. Did I do that correctly? And then we'll go ahead and divide to get y prime alone. It looks like y prime equals And so we got our negative 2 minus 3x squared y to the 5th all over 5x cubed y to the 4th. And I notice x's in both this term on top and this term on bottom. Can I reduce those x's?
No.
No, this first term, negative 2, included in the sum or difference, doesn't contain any x and y factors, so I cannot reduce any x's or y's. This is my fully simplified expression for y prime. Everybody, thank you. Don't, yes. Words to live by. Thank you, Brandon. So what I want you to go ahead and do is take a look at your expression for y prime right now, and then raise your hand if you have the same thing. So who had your y prime generation correct? Way to go, you guys. Let's go ahead and use that now to generate our slope of the tangent to the curve at a point. So we'll go ahead and evaluate this at my point of concern because we're working towards our equation of our tangent line. And you guys have done this now the past 3 Bellworks. By golly, I know that we're not going to have trouble generating the equation of tangent line algebraically anymore. So we've got x sub 1 would be given by 1, y sub 1 would be given by 2, and the slope of my tangent line will be given by y prime at the point 1 comma 2. Let's go ahead and do that now. Negative 2 minus 3 times x coordinate squared times y coordinate to the 5th. Yikes. All over 5 x coordinate cubed y coordinate to the 4th, and we'll evaluate when x is 1 and y is 2. How do we do? And we're working, oh gosh, negative, what is this, 32, 1, 3, 32, 96, negative 2, negative 98, so I'm getting negative 98 over 5, 10, 80. And I'm not throwing down my grapher onto the floor in frustration and stamping on top of it. I'm staying strong. I'm going long, and I'm getting negative 49/40ths. Raise your hand if you got negative 49/40ths for the slope of your tangent. Negative 49/40ths. Yes. And so we're all ready for our y minus y sub 1 equals m times my quantity x minus x sub 1, where my x coordinate was 1, my y coordinate was 2, and my slope of the tangent we just determined was negative 49/40ths. Take a look at your equation of the tangent line and raise your hand if you had the correct equation of the tangent line algebraically. You do that algebraically. Uh-oh. So let's go ahead and see then if this equation of the tangent line does in fact touch the curve at the point 1 comma 2. In order to do that, we'll have to rearrange my original expression for y. And so if my original expression was x cubed y to the 5th plus 2x equals 34, what will I have to do in order to enter that in my calculator? So what will I have to do before I can enter that into my calculator? Allie?
You have to make sure it's an explicit function instead, so you have to make sure the y is on one side.
Absolutely. So it looks like we've got some work to do. It looks like we'll have to subtract over. We'll have to subtract over the 2x and then divide by the x cubed. And then we'll have to undo that 5th power, right, by taking the 5th root of both sides. And so before I can enter my calculator, I have to solve for y prime. It looks like I'm getting when I go to enter my calculator, I just want to make sure that I do quantity, right? I want to do quantity divided by so that I don't mess up, right? Brandon?
Oh, whoops, I almost forgot that that's an odd root, so you don't need to plus or minus that.
Absolutely, thank you. If this had been an even root, then we would need to consider both the positive and negative to get both the top half and the bottom half of our relation. Typically, these implicit relations, right, aren't functions. They're curves that don't pass the vertical line test either. We've seen what ovals and footballs and ellipses, right? But I agree with you. But because this is an odd, I think we're good to go. So let's go ahead and enter our function. Remember, we can pull up an nth root by doing math 5. So I'm going to tell the calculator what kind of root I want. I want a 5th root, and then math 5 for xth root, and then I'll tell the calculator I want the 5th root. Inside, I want a parentheses for my numerator, 34 minus 2x, close numerator, divided by, on the bottom I want x cubed, so x math 3. I could always use the caret, but I think the cubing shortcut key is pretty bomb, so I always do math 3 for cubing, you know, because we can. And I'll go ahead and see what that looks like. And so I've zoomed 6 to get a standard viewing window, and it looks to me like I've got, almost like a hyperbola looking function. And that's kind of suspect. So we think that it's going to be y minus 2 equals negative 40ths times quantity x minus 1. This is an example of a situation where I would not distribute through the parentheses and run the risk of missing up fractions and signs, right, positive versus negative, and having to get the y-intercept. Instead, I'm simply going to rewrite by doing one step. All I'm going to do down in my grapher is add over that 2. Then I don't have to worry about messing up with the parentheses, the distribution, the fractions, and the negative signs. And so in my calculator, I'll enter y1 equals negative 49/40ths times quantity x minus 1, and then just plus 2 at the end, right? That way I don't have to run the risk of making any mistakes. So in my y sub 2, let's go ahead and add that now. Negative 49/40ths times quantity x minus 1, close quantity, plus 2. Did I have any lag? Double taps, everything good? Awesome. So I'm going to pull that. And now I'm ready to see how we did. Going for 1, 2, going for 1, 2. By golly, that looks like a tangent to the curve at the point 1, comma 2. A quick trace, 1, enter. We'll jump the cursor on, and it appears as though my tangent line does in fact touch the curve at 1, comma 2. But, right, just to be double sure, we'll go ahead and do our draw numerical calculation by doing second program as draw, and I'm going to select the 5th option, tangent. And we'll ask the calculator to do the same thing that we did algebraically. And I'm going to draw a tangent at the point when x equals 1. So I'll tell the calculator that x equals 1, enter. And if we're right, my line still has to be overwritten by the draw feature. And by golly, we did have the correct equation of the tangent line, and we can see it right there. And so my calculator is telling me negative 1.2250000. If you go on your regular home screen and do negative 1.225, enter, math, frac, enter, what fraction should it give us? What fraction should that give us? I'm sure hoping it does. So negative 1.225. Negative 1.225, enter, math, frac, enter. Voila! Negative 49/40. We're good. Brandon.
Couldn't you just do negative 1.225 to frac?
Maybe. 2 frac?
Like, what I mean is like
frac. Without having to enter first.
Yes.
Yes, I think you can. I think you can do it in one step. Negative 1.225, math, frac. Voila! That's totally a time saver. That saved me an enter keystroke. Thanks, Brandon. What questions do you guys have about today's dollar? All right, so we've got rule. Annika.
Is there, is there a problem with doing it like instead, once you get the slope, you plug it into y equals mx plus b?
No, there's no problem at all. You're welcome to do that. Okay, you're welcome to do that. The reason that I do point slope form each time in our tangent line generation is because it lends itself naturally to an application called differentials and linearization, where the equation of my linear approximation comes right from point slope form. In fact, it looks exactly like this. And that's why I use point slope form, so that it's a natural progression for us to write our L of x for a linearization function at a particular point, because it comes right from point slope form. So that's why I use this all the time. The College Board uses this a lot too. But you can certainly do it with y equals mx plus b if your end result is this right equation of tangent line. Certainly. Other questions about today's dollar? Okay, then let's go ahead and take care of our mega OTL. We did have our 4-9 packet as part of our OTL. And that was included in the actual calendar in the table portion of your Unit 4 block. The answer key there was for 4-9 related rates problems. You had to click in there as opposed to being attached to the resource with the OTL number 7 at the bottom. So there were 2 separate things, but for a total of 37. So right now I'd like for you to staple half sheet on top of 4-9 packet on top, and then bookwork on bottom, all as a single smooch. What? No half sheet?
No,
Oh, if you're unstable, that's fine. Just whatever order you staple them, make sure that your infinite canvas score is boxed on the top page nice and big. You gain that infinite canvas score by considering the number you complete out of 37, please. In pencil, divide, enter, multiply by 2. And let's box that infinite canvas score nice and big on top. Any order for staple? Whichever order you stapled, please make sure that your name, first and last, 2A, and number 7 are clearly labeled on top. And there's a staple on the side table as well. Are there no staples in there? Well, there's staples in this one. Have you named that one?
Oh, and then we bring it over. Just came back. Wow. This is so nice.
Okay, ladies and gentlemen, go ahead and pass those from the back to the front, please. Front rows, make sure they're facing the same direction. I appreciate your help. And now we're stocked with staples.
Just these little moments.
That's today's homework, not
Everybody good with number 7? If you did it, number 7? Okay, so we've got our Moodle discussion forum post this week, and many of you are off and running with some great posts. We've got examples of the beach ball manufacturer. We've got examples of animals in a shelter with a kennel. We've got some great tips from Subway in denominations of dimes and quarters. So we've got some great examples of some implicit relations. Make sure you check that out and get a hold of those easy 5 points outside of regular class. And not only is that an opportunity to interact with the content we're learning in class in a different manner with your classmates, but it also is a great way to earn extra points to kind of pad your grade aside from any test or quiz scores. Like your rules quiz. So that's great, and I want to share it with you. I'm going to go ahead and pause the recording, and then I'll pass that back to you so you can see exactly how you did. It was no surprise what was going to be a job. Okay, ladies and gentlemen, so what I want you to do is think back to Michaela and Jackie's experiment. So we had the CBL data, right, that we used from several years ago, and we generated data for the distance between the base of the ladder and the barn, and the top of the ladder and the ground. And so what quantities were changing in that problem, and I think we'll go ahead and make a picture. So we had and obviously in Wisconsin we have a red barn. When we'd have a red barn. And here's our ladder. Okay, so what quantities were changing in our problem, right? What quantities were changing in our problem? Jake?
The distance from the top to the ground, from the top of the ladder to the ground, and the distance of the bottom of the ladder to the barn.
Absolutely. And so if we let X represent that horizontal distance from the base of the ladder to the barn, thank you, Jake, and Y represent that vertical distance from the top of the ladder down to the ground, then both X and Y were changing, right? They were both changing with respect to time, and that's when we have a related rates problem. And so when we have two or more variable quantities that are related and are both changing with respect to time, we've got an opportunity to utilize our related rate strategy. And that's what we're going to practice doing today, and we're going to follow on our through problem situations all the way to completion. So we're not going to just stop, right, like we did with our 4-9 related rates packet with Terrence and Phoebe, or the classic Star Wars scene. That was pretty sweet. And we're going to go all the way and figure out the answers. And so the key here is connecting what we've learned about implicit differentiation, like our Bellwork, and now related rates differentiation. That is to say, both X and Y were changing with respect to time. As the ladder slid down the barn, right, both X and Y were changing with respect to time. Therefore, to get their rates of change involved in the problem, we'd have to differentiate each term with respect to time. And we did this at the end of last class. Going term by term, the derivative of x squared with respect to time is a chain rule. Exponent times the base raised to 1 less, and then times the derivative of the base. What's the derivative of x with respect to time? Well, that's my dx dt. There's my Leibniz notation for the rate of change, the instantaneous rate of change in x with respect to time. Plus, the derivative of my y term with respect to time is another chain rule. The derivative of y squared with respect to time is exponent times the base raised to 1 less times the derivative of the base. What, pray tell me, is the derivative of the base with respect to time? That's the dy dt. That's the instantaneous rate of change in y with respect to time. And on the right-hand side, still a constant. The derivative of any constant with respect to time is 0. And so we differentiate term by term. Now we'll be able to answer questions like, at the instant when the base of the ladder is 6 feet from the wall, how quickly is the top of the ladder sliding down? If we want to know how quickly the top of the ladder was sliding down the wall, would I be trying to find dx dt or dy dt? Which one would that be? Annika? dy dt. And so, depending upon what our original question is asked, we could rearrange this and solve it for, right, one of the variables, and that's what we're going to do today and answer the questions as asked. All right, so for our warm-up today, I want you to write down with your partner as many of these physical formulas as you can from memory. We're going to have a little competition here. So we're going to go ahead and write down the formula for as many of these as you can. We're going to go ahead and give you 2 minutes, which should be ample opportunity. And you can use your partner. Oftentimes our related rates problems involve real-world situations, right, that are geometric in context. And so we can think about what kind of formulas are represented by each one. People are stalling out. Yeah, people are stalling out. I mean, not you. I'm just saying people.
For cubing, we said that's where the area of one of the surfaces I no. Volume. No, you don't remember the volume? 4/3 higher. Did you get the code? Higher squared times
Awesome. We can't hear the timer because we got the USB plugged in for the microphone for our recording, but time is up. And so let's see. I saw some groups had all 5. That's impressive. I saw lots with 3 and lots with 4. Let's go ahead and share. So what's the volume then of a sphere? And we'll go ahead and use variables v for my volume. What did you get for that, Anna?
Volume v equals 4/3 pi r cubed.
Raise your hand if you got the same as Anna. V equals 4/3 pi r cubed. Nice job. Good. Pythagorean theorem. So what does Pythagorean theorem look like? Paul?
A squared plus b squared equals c squared.
Awesome. Where A and B are the leg lengths in a right triangle and C is the hypotenuse. Surface area of a cube, right? Surface area of a cube. What would that look like? Riley?
It's 6 times the side length squared.
So we could do S equals 6 times little s squared, where big S is the surface area and little s is the side length of my cube. Nice job. This is like a 6-sided die, right? A 6-sided die like we play in Monopoly or Yahtzee. All right. So the surface area of a sphere. Ooh, I heard someone talking about a geometry investigation where we had the orange and you peeled the orange, right? And we tried to get a connection. We should do more stuff with food in here. Right? Yeah, what's going on? We need more stuff with food in here. Winning group, okay. So, field trip to Warmup, let's go. So, surface area of a sphere, so who's got that? Who remember what the surface area of the sphere was in terms, Quinn?
4 times the area of the circle, so 4 pi r squared.
4 pi r squared. Raise your hand if you also have that. Does anybody else have that? So just a couple. All right, make sure you get it down. So the surface area of a sphere is actually 4 times the area of a circle, which is 2-dimensional, with the same radius. That's awfully interesting. And then the volume of a cone. I saw some interesting attempts at this. So yes, there is a fraction like our volume of sphere. So what do we have for that, Riley?
8 pi r squared divided by 3.
So
No, higher.
yeah. No. We want 3 dimensions.
I had it right.
So, yes, we need 3 dimensions, and so 2 of them count with my radius squared, and then another 1 with my height. So we've got 1, 2, 3. We've got a cubic, so that's a space shape. Good job, Riley. Jake.
So what are you finding if you don't have the 1/3? Because if you do 2 pi r squared times height, that's a cylinder.
Cylinder, yes.
But what are you finding without just?
That would be a cylinder.
That would still be a cylinder?
That would be the volume of the cylinder. So base area times the height would be a circular cylinder.
Okay.
Yeah, absolutely. A third of that, and that's actually an interesting activity too, right? If you went ahead and took a given cone, right, and filled it up 3 times with water and filled up a cylinder with the same radius and height, it would fill it exactly. And so that's interesting. That 1/3 is very interesting how that relates with our volume and space shapes. In any case, the point of that was to get us thinking geometrically. Oftentimes these related rates problems involve a geometric formula from our problem situation. Our strategy is going to utilize drawing a picture to represent the written description, labeling that picture with the appropriate variable quantities, and then relying on our implicit differentiation, right? To go term by term, differentiating each term with respect to time to get our rates involved. Let's go ahead and take a look at our strategy then. So for our related rate strategy, which I'll be calling on you throughout to make sure that we're practicing with our steps and getting a good strategy, is to first read the problem carefully and then write down the known rates and what you're trying to find. On the Unit 4 test, you can get points just for writing down what rate you're trying to find, right, and what rates are known. That's what's going to drive our problem, including our eventual relation and differentiation. And so it's important that we're able to identify the known rates and the rates that we're trying to find. 2, we'll draw a picture and label with relevant quantities. If some quantity is changing, it has to be labeled as a variable. Only if a particular quantity is constant throughout the course of the entire problem can we ever label with a constant. And so, if a quantity is changing, it has to be labeled with a variable, and you can't fill in a number to your picture. Write a formula that relates the quantities in the question, and this is my favorite step. So this is where we draw on all our wealth of knowledge from geometric formulas that we've seen in the past. We're going to try to limit the variables in our formula to only those quantities that are changing. That'll be less variables to differentiate with respect to time and a simpler derivative. 4, we'll differentiate both sides of our formula with respect to time. That's similar to implicit differentiation. And then lastly, we'll solve for the desired quantity. And only then will we plug in any moment in time values, like you were doing in your 4-9 related rates problem activity last time. Only then will we plug in those at instant in time, those values at the end. Don't forget to include your appropriate units. So let's go ahead and practice this strategy now and settle different problems. First, let's suppose that a spherical balloon is being filled so that its volume increases at a constant rate of 100 cubic centimeters per second. So we're thinking about this spherical balloon being inflated such that it's filling at a constant rate of 100 cubic centimeters per second. The question is, how fast is the radius increasing when the diameter is 50 centimeters? So let's go ahead and take a look at our strategy. First thing, we want to read the problem carefully and write down the known rates and what we're trying to find. So we're going to write down the known rates and what we're trying to find. Let's take a look at our problem again. In terms of this problem, we know one rate. Sometimes, right? Sometimes it's helpful to do step 1 and step 2 together. So we'll go ahead and get a picture involved here. If we're assuming a spherical balloon, then we can draw our balloon. I'll do my best. I'll do my best here for three-dimensional. We could label then this as my radius. And I've been working years and years on trying to perfect this. If we did, I saw when girls wrote notes, they include these little like reflection star things there. That's a sphere and that's reflecting the light. Ah, everybody see the three dimensions? Nice, nice touch. Thank you, Savannah, thank you. So there's our spherical balloon. So what's our known rate, right? What's our known rate then, based on the spherical balloon? Well, it's being filled at a constant rate of. And so what with Leibniz notation would that be? What quantity would that be? Riley?
Yeah, centimeters.
Yep. What's changing?
Yeah, the volume.
The volume. And how can I write that as a rate, right? How can I use Leibniz notation to write that as a rate? Would that be a dAdt, a dxdt, or a dydt? Well, none. It would be what? dVdt. And so we'll go ahead and write our rate in Leibniz notation, and that drives home the fact that the volume is changing with respect to time. So my known rate is dVdt is equal to 100 cubic centimeters per second. There's my known rate. Now we're going to write down what we're trying to find. So our known rate is dVdt is 100 cubic centimeters per second. And what rate are we trying to find? Well, we want to know how fast is the radius increasing when the diameter is 50 centimeters. So what rate are we trying to find, right, with Leibniz notation? What would that be? Kobe?
dr dt?
Absolutely. We want to find dr dt at the instant when the diameter is 50 centimeters. So we want to find dr dt when my diameter equals 50 centimeters. Okay, so step one, read the problem carefully, write down the known rates and what we're trying to find. Step two, we're going to draw a picture and label with appropriate with appropriate variables. If a quantity is changing, it must be labeled with the variable. Notice how I didn't put 50 or 25 in my picture, right? That's a particular instant. That's just a snapshot at one moment in time. The radius is changing throughout the problem as it continues to inflate. So it does not make sense to label anything as 25 in my picture, okay? Great. Next step, write a formula that relates the quantities in question. Try to limit the variables in our formula to only those quantities that are changing. We need our formula to include letters that are in our rates. So we need our formula to include V's in it and R's in it. Is there a formula that relates V and R in this problem situation? Absolutely. Didn't we just do that in our warm-up? Right? So what formula am I going to use that relates the quantities in this problem? Brandon?
That would be V equals 4/3 pi r cubed.
Absolutely. So V equals 4/3 pi r cubed. There's our relationship between the variables that are in our rates. We're going to go ahead and differentiate both sides of my formula with respect to time. This is our implicit differentiation, where every time I differentiate a variable quantity, it's going to spit out a times the derivative of the base, dx dt, dy dt, dv dt. Let's go ahead and differentiate both sides with respect to time. So we'll go ahead and differentiate both sides with respect to time. When I do that, I get the derivative of volume with respect to time. What's that? There's my dv dt that we wanted. There's dv dt equals the derivative with respect to time of 4/3 pi r cubed. Oh goodness. Well, we'll grab that constant multiplier. That 4/3 is just a constant multiplier. It'll be there multiplying my derivative. So I'll leave that out front. And then I'll go ahead and differentiate pi r cubed. Pi is another constant multiplier, so that's out front. So we're just stuck differentiating r cubed with respect to time. No problem. That's a power rule. So we've got exponent times the base raised to 1 less times the derivative of the base. What's the derivative of r with respect to time? dr dt, and there's my other rate that we needed. That's the one that we're going to eventually find. So we've gone term by term. Well, there are only two terms, one on each side. Our constant multipliers stay out front, and then we can rewrite this to make it a little bit prettier. So I'm going to go ahead and rewrite this as dv dt equals, we can cancel out the 3's, and I get 4 pi r squared dr dt. And I'm confident in my derivation with respect to time. So I get dv dt equals 4 pi r squared dr dt. Now let's focus in on what we're trying to find. Number 5 says, solve for the desired quantity, substitute in the given information, and answer the question that was asked with the appropriate units. Notice how we haven't done anything at all with that moment in time value, that moment in time when the diameter is 50 centimeters. We'll only do that at the very end. In fact, I'm still going to solve for my rate in question that we're trying to find. I'm still going to solve for that first and only plug in at the very end. So what were we trying to find? We were trying to find dr dt, how quickly the radius was changing with respect to time at the instant when the diameter was 50. So I'm going to solve for what here? We're going to solve for the dr dt. So to do that, it looks like I'll divide, and I get dr dt is given by dv dt all over 4 pi r squared. So I solve for dr dt in this case by a one-step division. And now, and only now, will I substitute in my moment in time, my instant. So dr dt must be given by dv dt. What was dv dt? That was my 100 cubic centimeters per second. So 100 goes into that over 4 pi r squared. And r is the radius at the instant, the moment in time when the diameter equals 50. Well, the diameter equaling 50 is the same as my radius equaling what? 25. And so I'm going to put in 25 for r. Awesome. And we'll do a little simplification and math fracking. Or I'll recognize that 25 squared is 25 times 25 times 4 is 100 times 25 and cancel out the 100s. Either way, I get 1 over 25 pi. You guys getting 1 over 25 pi? And what would the appropriate label? What would the appropriate label on that dr dt be? Well, we can think back to our rate of change units. Remember, rate of change or derivative units are always given by y units over x units. Or in this case, look at my Leibniz notation. That reminds me it's radius units over time units. So this would be measured in centimeters per second. So this must be centimeters per second. Awesome. So what have we figured out? We want to answer the question that was asked, including the appropriate units. So at the instant when the diameter is 50 centimeters, the radius is increasing at a rate of 1 over 25 pi centimeters per second. Is the radius increasing or decreasing? It's increasing because it's positive. That makes sense. We're inflating the balloon. The radius is increasing. Is it increasing quickly or slowly? Slowly, and that makes sense too. If we have a big balloon, even though we're pumping in 100 cubic centimeters per second into that big balloon, as the balloon gets bigger, right, it encompasses a larger volume, and so a constant rate of change in volume is going to result in smaller and smaller increments of radial increase. And that makes sense when you blow up a balloon. Notice how you have to start putting a lot more air into that balloon, right, in order to make it grow as you get towards the end of it, as it gets big. So that's kind of interesting. All right, let's go ahead and take a look at another. Again, we'll be applying our strategy, so be ready to share what step in the strategy we're dealing with, and you can flip back as needed. A ladder is 10 feet long and rests against a vertical wall. If the bottom of the ladder is sliding away at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? What does step 1 ask us to do from our strategy? Savannah?
Find variables. Label the variables.
Oh, yeah, we want to, more specifically, we want to write down the known rate and the rate that we're trying to find, right? That's going to determine what variables we want to be using. So I want you to actually write down the known rate and what we're trying to find. So let's go ahead and read the problem carefully and see if we can't write down the known rate. Well, I'm with you, Savannah. I think we're going to have to define our variables if we're going to get a rate. So we can do 1 and 2 together here. It looks like we need our ladder, and our distance from the base of the ladder to the foot of the wall, and our height of the top of the ladder to the ground. So now that we have our variables, what's our known rate, right? What's our known rate in terms of the variables that we have? Right? What's our known rate here? Hayden?
dx/dt equals 1 foot per second.
Absolutely. As we've drawn it, we know that our known rate is dx dt equals 1 foot per second. So our known rate, I'm going to write that down. Is dx dt equals 1 foot per second. Awesome. And then we'll write down what we're trying to find. And so we're going to write down the rate that we're trying to find. In terms of the variables in our picture, what is it that we're trying to find? Preston?
The distance from the bottom of the ladder to the wall.
Is that what we're trying to find? What rate are we trying to find? So what's our question asking us?
Oh, how fast the top of the ladder is going.
So in terms of our variables, what rate would that be with Leibniz notation?
dy.
Yeah, dy dt. I know. Everyone wants to share. Me too. High School Musical. All this together. So we want to find dy dt, right? Find dy dt is what we're trying to find at the instant when the bottom of the ladder is 6 feet from the wall. So we want to find dy dt when what's true? Heavy?
X equals 6.
When x equals 6. Now that's a moment in time. That's an instant. So we're not going to plug that in any formula until the very, 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 very end, right, for our final evaluation. But we're trying to find dy dt at the instant when x equals 6. Thank you, guys. Good job. All right. So now we've got our step 1. We've gotten our step 2 because we needed step 2 to get our step 1 in this case. And now we're ready for step 3. So what does step 3 ask us to do in our strategy, Marissa?
Write a formula with like our variables.
Absolutely. So we'll have to write a formula, right? We'll have to write a formula with our variables, with our changing quantities. In order to do that, we can rely oftentimes on our geometric relationships that exist in the problem, and that's why we did our warm-up. Evie?
Should we have labeled the hypotenuse as 10 because it doesn't change?
That's a great question. So if we're going to relate our x and y in a formula, right, Pythagorean jumps to mind, but we need that hypotenuse length. Now that could be c, right? It could be z, but we want to limit the variables in the problem to only those quantities that are changing. Evie suggests that we can label this with a constant, right? Raise your hand if you agree that we can label that constant, a constant. Raise your hand if you think we need to label it with a variable. Z, C, no? I agree. Evie, let's go ahead and label that with a constant because the ladder length does not change over the course of the problem. Good job. So because the ladder length stays constant at 10 feet throughout the duration of the entire problem, we can label it with a constant. Let's limit the number of variables to only those quantities that are changing. Nice job. So what formula relates x, y, and 10? Anna?
Is it? Oh, is it 10 squared equals x squared plus y squared?
Absolutely. So if we have a right triangle, right, a right triangle, then we know the Pythagorean theorem can be used to relate the side length. So x squared plus y squared equals 10 squared. Perfect. Thank you. All right. Step 4. We're now ready to differentiate both sides with respect to time. So we're going to differentiate both sides with respect to time. And this now looks like Michaela and Jackie's experiment, doesn't it? So we'll differentiate both sides with respect to time. The derivative with respect to time of x squared is 2x dx dt. There's our rate. Plus the derivative of my y term. Y squared with respect to time is exponent times the base raised to 1 less times the root of the base. That's 2y dy dt equals the derivative of a constant. 10 squared with respect to time is 2, 0. 0. Yes. Love it. Okay, so we differentiate both sides with respect to time. And now, what's our step? Our step 5 asks us to do? We'll solve for the desired quantity, right? And substitute in the given information lastly. We haven't done anything with that moment in time data until the very end, and I'll only plug that in after I've already solved for it. So what we were trying to find, Preston told us we were trying to find dy dt. So that's what we're going to isolate. So we'll go ahead and isolate dy dt. How will we do that? Well, it looks like we'll have to subtract over the x term, negative 2x dx dt, and then divide by, right, divide by our 2y. So if we divide by that 2y, it looks like we get an expression for dy dt. Divided by 2y gives me negative x dx dt all over y. So I'm getting opposite of x dx dt all over y. Are you guys getting that? Did I mess up with the constants? Are we good? All right. Now and only now I plug in my moment of time data and information to figure out what dy dt is at that instant. So let's go ahead and see. At the instant when x equals 6, I can plug in 6 times dx dt all over y. I already had the dx dt was 1, so I'm feeling pretty good about that. I know that at the moment when x equals 6, x is 6, but I'm missing y, and so I don't know what y is at the instant when x equals 6. Or do I? What can we do to figure out y when x equals 6? Riley?
10 squared minus 6.
Yeah, we could go back to our original relationship. We know that 10 squared minus 6 squared equals y squared, and then take the square root. So at the instant when x equals 6, I can figure out what y is, and I'll do that with the Pythagorean theorem. So when x equals 6, y equals the square root of 100 minus 36 is 64. The square root of 64 is 8. So then and only then can I plug in 8, which means that it looks like dy dt is given by negative 3/4. And what would the label on dy dt be? Well, y is measured in feet, t is measured in, so dy dt must be in feet per second. Good job. Uh-oh. Did we mess up? We got a negative. Can we have a negative rate?
No.
Yeah. What does y represent in the problem?
The distance.
The height of the top of the ladder to the ground. And the problem is the base slides away from the wall. What's happening to y? It's decreasing. So it makes perfect sense to have a negative dy dt. What did the problem ask though? How fast is the ladder? So we can make an argument for, yeah, we could say, right, the ladder's sliding down the wall at a speed of 3/4 feet per second, right? But dy dt itself is negative, and that makes sense because the distance y is decreasing as the base of the ladder slides out from the wall. And so this is a situation where I would put dy dt equals negative 3/4, so sliding down at a rate of 3/4 per second. Three-fourths feet per second. What questions do you have about our ladder problem? Okay. Then let's go ahead and take a look at one that's a little bit more complicated. And so we've seen two different situations where we had a single variable, right? A single variable on which my rate involving the variable in question depended. Now we're going to take a look at a little more complicated scenario. A water tank has the shape of an inverted cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Let's go ahead and process that for a minute. So we've got a water tank in the shape of an inverted cone. So we're thinking, right, we're thinking not the blocks cone, but like the snow cone. So with an inverted cone. So we've got our snow cone orientation, right? Water is being pumped into that tank at a rate of 2 cubic meters per minute. So we've got a water level in here that's rising as time goes on. And we want to find the rate at which the water level is rising when the water is 3 meters deep. Is this... Did they just tell us how quickly the water level was rising? Did they tell us how quickly the water level was rising? No, they told us
how
fast it was being filled, right? They told us a change in volume. We're pumping water in, right, at a change in volume, but we want to know a linear change. We want to know the water level as a height, right? How quickly that's changing. So let's go ahead and label some variables and let's write down our known rate and what we're trying to find. That's going to drive our problem. So we have our known rate and what we're trying to find. What rate are we trying to find? Okay, so as I take a look at this problem, what formula is going to make sense? Well, it looks like we need a volume and we need a height, and so I want my known rate in terms of Leibniz notation. What's our known rate here then? What would that look like for this given information? Who's got it? Eddie?
dV dt equals 2 cubic meters per minute.
Awesome, thanks. Let's do dV dt equals 2 cubic meters per minute. Thank you. What rate are we trying to find? So what rate are we trying to find? Well, for that, we probably need some more stuff. If we want the rate at which water level is rising, we need a variable to represent the water level. So what might make sense for that? We could do maybe H. If we want to do H for height of water. And V then would be volume of water. So what else would we need? Well, we still need, we need radius of my little water cone that's changing, right? So I need an H and I need, gosh darn it. So we're trying to find dH/dt at the instant when the water is 3 meters deep. So when what? H equals 3 meters. Good. Awesome. So we're going to find dH/dt when H equals 3. Okay. Step 3, my favorite step. Look back at your strategy, please. What does step 3 ask us to do? So what does step 3 ask us to do? Emily? Good. So we've got to write our formula that involves a V and an H. And to do that, we might need here this R. So what formula will we use for this one? Right? What formula will we use for this one? Michaela?
The volume of a cone is V equals 1/3 pi r squared H.
Awesome, thank you. All right. So we've written our formula that relates the quantities in question. That's good. However, what do you notice about our volume formula in this case versus our volume formula in the first case? And what's different about our formula now? Riley?
We have 2 variables.
Yeah, we have 2 variables, and that's no problem for us. With implicit differentiation, we can handle any number of variables on the same side mixed together. It's just that what rule would we have to use when differentiating the right-hand side? Product rule, right? Yes, we'll use chain rule every time we differentiate a quantity with respect to time, but within the product rule, because we've got pi r squared times h. So we can certainly do that. However, every time we differentiate an h term, it's going to spit out a what? a dH/dt, that's good news, because that's what we're looking for. But on the flip side, every time we differentiate an R quantity, it's going to spit out a what? dRdt. Is dRdt a known rate? Is it something we're trying to find rate?
Nope.
Is it the moment in time rate? Or moment in time value? No. And so we, if we can, want to get rid of which variable in that formula? We would like to get rid of the R and write it solely in terms of H. If we could do that, then we wouldn't have to worry about any dRdt's that we spit out that we don't know anything about. So to do that, we are going to have to utilize relationships in the problem that exists, right? That hopefully will allow us to rewrite that as a formula of volume depending solely on H, not both H and R. Is there anything else we could use to our advantage? Monica?
Isn't the R, like you drew it like with the water, but isn't it on the top of the circle?
That's a great question. Did you hear Annika? She said, didn't I draw the R down here in the water, but isn't there the radius right on top of that circle, on top of that cone? What do you guys think?
Well, we have a given radius.
Yeah, we have a given radius that's on top of my cone, right? Is that changing? No, and so like Evie suggested in the last problem, we could label the radius of the tank as a constant. Let's do that. So let's label the radius of the tank as a constant. What is the radius of the tank?
2 meters.
2 meters. Is there anything else that's constant that might help us out? The height of the tank is unchanging, right? We could label that. What can we label the height of the tank?
4 meters.
And that's an important question then. Do we even need this R at all? What does R represent in my picture?
The R is
Part
in
of
the
a similar
water.
triangle.
In my picture, the R is the radius of the water cone. Is the water cone radius changing?
Yes.
Yes. Do I need the R?
Yes.
Yes. Is the H in my problem, is the height of my water cone? Is the height of my water changing?
Yes.
Yes. Do I need the H?
Yes.
Yes. So this is appropriately labeled, but Riley has keyed in on what's going to allow us to rewrite our formula with just H's. Notice the relationship when I draw in this dashed line up to the top. Don't we have a triangle within a triangle, right? Don't these share 2 right angles? Don't they share the same angle, right? And so what kind of triangles do we have? The water triangle and the tank triangle. Not congruent, but similar. We got similar triangles. Remember, congruent is same size and shape. Similar is same shape, right? So we can write a proportional relationship between R and H and 2 and 4. No matter the height of the water level, it must adhere to the same relation, that is, R is to H just like 2 is to 4. Or R is to 2 just like H is to 4. However you want to write that proportion. So I'm going to go ahead and utilize that to my advantage. I could say that R is to 2, just like, and if I chose to start with this as my starting statement, R is to 2, then what must my other side be? H is to 4. Good job. And you can write this 6 different ways. I mean, you could write it however you see it. But what, in the end of the day, we want to solve for which variable in terms of what variable? Well, we want to get rid of the R's in that formula, so we better use this relationship to solve for R and rewrite in terms of H. So let's go ahead and rearrange this. Go, Gadjarm. R must equal 2H over 4, which in turn must equal H over 2. So I'm going to go ahead and rewrite the R in my formula as H over 2. No matter how high the water level is, I know that the radius of the water cone is always half its height. Because the dimensions of the tank to which my water cone must adhere, right, the radius is always half of the tank height. All right, let's go ahead and rewrite it. Here we go. V equals 1/3 pi radius squared H. What is my radius in terms of H? H over 2, comma baby, which means my volume V is given by, looks like H over 2 squared is H squared over 4, times H is H cubed over 4, times the 1/3 is h cubed over 12, and times the pi on top, I'm getting pi h cubed over 12. Let's go ahead and make sure we did that correctly. I'm getting pi h cubed over 12. So we do that correct? H squared h cubed, pi's on top, and then the 4 on bottom times the 3 on bottom is 12. I think we're good. Hey, step 4. So what does step 4 ask us to do in our strategy? Right, what does step 4 ask us to do? Emily? Good, let's do it. So we'll differentiate now both sides with respect to time. Go guys arm. The derivative of v with respect to time is dv dt equals, going to pull my constant multiplier, pi over 12 out front, and then differentiate h cubed. Can I differentiate h cubed with respect to time? You bet your boots. The derivative of a power function is exponent times the base raised to 1 less times the derivative of the base. What's the derivative of the base? dh dt, and that's what we were after. In my derivative of the equation, what quantity were we trying to find, right? What quantity were we trying to find? Paige? Which were these rates we were trying to find? dH dt, absolutely. So let's rearrange that for dH dt. In order to do that, we could do some reducing. It looks like that 3 over 12 is the same as 1 over 4. So I'll multiply it to 4 over. I'll divide by the pi h squared, and I'll get my dH dt alone. So we can do that in 2 steps, right? It looks like we'll times the 4 over. We'll divide by pi h squared, and I'm getting 4 dv dt over pi h squared, and verify that I've done that correctly. All right, are you guys getting that? So we can reduce the pi over 4 and then times by 4 over pi. We can divide by the h squared, and then I'll end up on bottom. And now and only now can we plug in our moment in time information. Here we go. So at the instant when the height of the water is 3 meters, dH dt is given by 4 times dv dt over pi h squared, where h is 3, and dv dt is my original rate, which was 2. So it looks like we're getting 8 over 9 pi. And an appropriate label for dH dt would be what? What will this be measured in?
Meters per minute.
Meters per minute. Linear units for h over minute units for t, so meters per minute. Awesome, you guys. That was super sweet. Okay, so some easy things to check. Should my dH dt be a positive or negative quantity? Positive, is it? Yes, so that's good news. So it looks like my water level is rising. Awesome. So the key here when we had multiple variables was to use relationships in the problem. In this case, it ended up being similar triangles, right? To rewrite it with as few variables as possible. Try to limit my variables to those quantities that are changing that I want to find out about, like dH dt, right? We could have equally solved this for h in terms of r and plug back in, but then we just have r's in there. And we wanted to have h involved so we could find dH dt. Awesome work, you guys. All right, so let's go ahead and put it together. Let's summarize our learning for the day in closure. When solving a related rates problem, all terms are differentiated with respect to, don't call out, just write it in. When labeling a picture, when is it okay to label a quantity with a number instead of a variable? And then if too many variables exist in my formula, which should you try to eliminate? These are all great questions for our related rate strategy. I'm looking for a written response on each of your papers, and please be ready to share on the whiteboard. Okay. Please be ready to share your response with the class when I call on you. When solving a related rates problem, all terms are differentiated with respect to, Brandon?
That would be time.
Time, absolutely. So we can differentiate each term with respect to time, knowing that each quantity is going to spit out a drdt, right? Or a dvdt, or a dxdt in accordance with the chain rule. When labeling a picture, when is it okay to label a quantity with a number instead of a variable? Tess?
When the quantity is constant throughout the whole chain.
Absolutely. And so only when the quantity is constant throughout the entire problem. Only when that, like the ladder. The length of the ladder didn't change throughout the whole fall, right down the wall. So only when the quantity is constant throughout the entire problem. Oh my. Constant. Constant, no, constant. And lastly, if too many variables exist in your formula, which should you try to eliminate? So if we got too many variables in there, which should we try to eliminate? Allie?
The one that you're not solving for.
Yeah, the ones that you're not trying to solve for or find the rate, right? We were trying to find DHDT, so we tried to get rid of the R's because that wasn't involved in our rate that we're trying to find. So what did we say one's not trying to solve for? And I'm going to add in the original question. Because we ended up trying to solve for R in terms of H so that we could get rid of the R's and just have H's. Awesome work, you guys. Okay, so what possibly could be with our counter here? It feels like we've had a great full lesson that's come full circle. We talked about the hamburger, right, with the bun. We've got our Bellwork for the top, and then we've got our meat of the lesson in between, and then we just finished up with our closure, the bottom of the bun. What in the world can we be doing with our 14 out of 36? I'll tell you. Because it's that special time. No, not that time, Kobe. It's time for a guest appearance. Haven't seen him in a while. It's time for mental derivative. It's a good thing we learned our derivative rules. So let's get ready. Here we go. Everybody get ready. I'm going to use the random number generator to call on you. I'm going to use the random number generator to call on you. Okay, let's everybody get going, and we're to 21 minus Sammy.
I'm 21, Sam's 20.
Gotcha. So we're 1 to 21. Get your number ready. Here we go. Mental derivatives. The derivative with respect to x of negative 4x to the 9th. Get ready. Number 15. Survey says you are correct. Nice job. Very nice. Very nice. 5x to the 12th differentiates to number 16.
60x to the 11th.
You're correct. Very nice. Okay. 1 over x cubed differentiates to number 10.
Negative 3x squared over x cubed to the second. So x to the 6th, which simplifies to 3 over x to the 4th.
Oh my God! Way to work it out! Very nice, Akira. That was good stuff. Plus 10.3. Plus 10.3 points. Derivative with respect to x of 1 over x squared. If you want to use paper, you can. I'm just going to call on you. You're ready. Number 20.
Wait, is that me or is that? I thought.
I think it's Emily. No. Oh, is it?
18, 19, 20, 21.
No, I'm 17.
Oh,
Wait,
I'm 19. She's
I'm
20.
18.
she's 20.
20. and
You're 21, 21.
21.
Oh, it's gonna be hard to call on Emily. She's 22 and I only did random number generator at 21. So we're gonna fix that right now. You're lucky this time, Emily. I'm watching you. Ready? Oh my gosh, number 22! Oh my gosh! Number 22.
Negative. All of the x.
Right, if we think about that as rewritten with a negative exponent, then it's easier to apply our power rule. Which in turn would be rewritten as negative 2, and x to the negative 3 can be rewritten as 1 over. Absolutely. So you guys see how if we rewrite that as a negative exponent, then it helps to apply the power rule more easily. All right, get ready. Derivative with respect to x of 1 over x. Noticing a pattern here? Get ready. Number 17.
Negative x over, no, negative 1 over x squared.
Sorry, so you are correct. Very nice. Derivative tangent of 3x. Oh, we know these. We have them memorized. I saw it. Most of us have these memorized. Get ready. Number 11.
X squared 3x.
3 secant squared 3x. Or is that John Beck? Good job. Listen. Derivative of secant of x squared. Number 21.
Okay. Secant of x squared times tangent of x squared times 2x. Or 2x.
Yes, absolutely correct. Good job. What's that? Derivative inverse sine of 4x. Derivative inverse sine of 4x. Number 20. That's Sammy. Number 2.
1 over the square root. Oh, wait, it's 4 over the square root of 1 minus 16x squared.
You're correct, listen. Very nice, very nice. Derivative with respect to x of pi cubed.
Is this one?
Number 18.
Oh, it's 0!
It's correct, listen. Derivative of pi to the x. Derivative of pi to the x. You can do it. Si se puede. Yes, you can. Number 8.
Natural log of pi times 20x.
I love it. Nice job. Good work with the exponential, Kate. Very nice. Plus 20. Derivative with respect to x of x to the pi. Number 16.
Pi times x to the pi minus 1 power.
Yes, you are correct. Good job. Very nice. Very nice.
That's a lot.
Derivative of cotangent of 2x plus 1. I know you know, but I know that you know cotangent. It's derivative. Number 20. Again. Number 22. Again. Oh, not the derivative of inverse cotangent, the derivative of cotangent. Absolutely. Good job. Good job. Let's thank. Derivative of ln of x cubed. There's an easy way, and there's a hard way. Number 12. Nice job. Way to handle. Way to handle. Derivative of ln of x to the 7th. Number 3. Nikki. Nikki.
Yeah.
Number 17.
7 over x.
You're correct. Very nice. Oh! Derivative of ln of x to the 101st power. Number 12. Again.
101 over x.
Good job. So if you bring that power down in front, it says the multiplier and then differential ln of x is 1 over x. Nice job. Way to go, you guys. Derivative of x is e to the sine of x. Number 7.
Sine of x, e to the sine of x. Oh, no, cosine of x. Sorry.
Right. Exponential itself times the derivative of the x1. Good job. Good job. And derivative. Oh, now inverse secant. Inverse secant of x. Goodness. Number 18.
So we're gonna have 1 over the absolute value of x times the square root of x squared minus 1.
Who are you? Who are you? Very nice. All right, that concludes our guest appearance. You guys can go and pack up. Great work today. Nice job. Memorize your rules because we might see a rules quiz. Oh, what's that? So this is your homework. Our homework is OTL number 8 half sheet, and then just do 1 to 7. We're gonna save numbers 8 through 13 for our review day. Guys, only do 1 through 7 on the packet, right? And we're gonna save the other ones for our review day work. 1 through 7 are ones that we should be able to handle at this stage in your lives without much trouble. After that, it gets a little bit more complicated, like the water cone ones. So don't forget OTL half sheet, and then plus numbers 1 through 7 only on the related rate sheet. Does that make sense? Awesome. I'll go ahead and stop the recording.